pi r squared, the area of a circle. Why? Why is the area of a circle the ratio of a circle's circumference to its diameter multiplied by its radius squared? Would you believe me if I told you that this leads to a fundamental theorem of calculus? Bear with me, but I'd like you to imagine a circle with an arbitrary radius, and I'd like you to calculate its area disregarding everything you know. To do so, you might say, okay, let me take a similar shape and I'll draw it in the circle and I'll calculate its area, and that would be a good approximation. But let me show you another approach. What we can do is we can take our circle and just draw more circles inside, creating equally spaced segments, each with a thickness, call it dr. And let's draw a few more circles, cover it up. Yeah, that's pretty good, right? And we take one of our segments and let's slice it. We'll roll it out flat. With a good approximation, we could say it's a rectangle. Now, being a shape that we know, we have its length being 2 pi r, the segment's circumference, and then its width being our thickness, dr. And being an area we know how to calculate, we simply do length by width and we get the area of that segment. Easy, done. Okay, let's do it for each segment. Take each segment and put them next to each other, each being taller than the other because they have their own radius respectively. And if you're asking me, this looks a lot like a triangle, but not quite. We have all this empty space. So what we're going to do, we're going to decrease our thickness dr, which allows for more segments to take up all that empty space, which allows us to closer approximate a triangle. And if all these little segments are representing our circle, we can just take what we know, the formula for an area of a triangle, and calculate the area of our circle. So the area of a triangle being half times base times height, where the base is our radius r and the height is the circumference of our circle 2 pi r, multiply by half, and we'll get that the area of our circle is pi r squared. And now we can say that the area of our circle is pi r squared without a doubt. I feel that it's very important that I just go over what we just did in a more detailed way. Initially we said, let us calculate the area of our circle by taking it piece by piece, which will allow us to get a rough estimation of our area. And then we saw by observation, we can refine our estimate by decreasing the width of our segments, allowing for more segments to take up that empty space, creating a better approximation. But what we did, we just took the limit as our thickness approached 0, or we made our thickness smaller and smaller to such a minute size that it's much easier to just say it's 0. And once we've done that, we just sum all the areas of all our segments to give us the true value of our circle's area. Alright, pause. You see this giant sideways M? This is a summation. This is saying I want you to add every area of your segments one by one. And see the part at the bottom? It's saying let's index every area by the letter I, starting at I equals 1 for your smallest area. And then the part at the top, the infinity sign, is your endpoint, saying that your index I will go all the way up to 1 to infinity. As we know, we have an infinite amount of segments as our thickness approaches 0, as we saw that we need an infinite amount of segments to fill up that triangle. Alright, back to the video. And if you haven't noticed yet, this is something you may have seen before or even learned. This is the essence of integration. This squiggly line, this is an integral. In mathematics, the process of integration is simply seen as how to calculate the area under a graph. Given a function, if one wishes to calculate the area under that graph, simply separate it into very small segments, so small in fact that the thickness appears to be 0, and calculate the area. But with functions and graphs that don't have areas that resemble familiar shapes, it can get a bit tricky. To do this, let's look at my car. Right? What if I told you that I can find the distance that my car traveled simply by observing how fast it went over a given time period? And let's say it looks something like this, right? Let's say it started off at 0 meters per second and then went up to 60 meters per second, back down to 0 meters per second, right? Mathematically, remember, speed is just distance divided by time. So rearranging, distance is speed multiplied by time. To make this a bit simpler, let's observe my car going a steady 60 meters per second for a 10-second period. And if we want to find the area under that graph to find our distance, it's simply just a rectangle where our length times our width is our speed multiplied by our time. 60 meters per second multiplied by 10 meters per second, 600 meters. Easy. So let's go back to our problem where our speed profile is a curve, which makes it a bit tricky, but we know the approach. Let us make segments under the graph which represent rectangles, where the height is the speed of our car at a given point in time, with the width being our time interval dt. Our estimate looks a bit poor, so let us decrease our time interval, allowing for more segments, which looks a bit better. And now let's go to the extreme, making our time interval infinitesimally small, so small in fact that it just looks like we have now shaded all the area under the graph. I recommend you understand derivatives before watching this next part, and if you need help, I've made a video on it which I'll link down below. We know that the area under the graph is our distance, yes? And we also know that a tiny change in distance, ds, divided by a tiny change in time, dt, is equal to our velocity. And with that, we can rearrange it and say that a tiny change in distance, ds, is equal to our velocity multiplied by our tiny change in time, dt. Equating over each change in time, dt, and taking the integral, we can say that our total distance traveled is equal to the integral of v multiplied by dt over our interval. So what does this mean exactly? Well, this mathematical expression is saying in order to find the area under any graph or the integral of any function, one must find the antiderivative of that function, or you must find the function which, when derived, gives you your initial function that you were trying to take the integral of. Let me show you an example just to clear things up and make it a bit easier for you to understand. Before I show you an example, there are two types of integrals which I must introduce that you will face in any test or an exam. The first integral you will probably come across is an indefinite integral. This is an integral where the answer they expect is an expression, not a numerical answer. The answer they want is that function at which, when derived, gives you your initial function. But it's important you add this plus c. If you don't add that plus c, you will lose marks in a question and you will maybe even get no marks for the question because there's an infinite amount of functions that can solve this expression. So it's very important you express that by writing this plus c. The next one you will see is a definite integral. This integral is one that requires a numerical answer because you're solving between two bounds, solving between an interval where your lower bound is your a and your upper bound is your b. And the way you solve this is by evaluating the function at which, when derived, gives you your initial function at the upper bound and then subtract it evaluated at the lower bound a. Now going to an example, I've tried to do something that will reflect what I've tried to explain in this video. Here we have our velocity is equal to our time multiplied by 5 take half our time, which represents a parabola over a 10-second interval. And looking at this, we can see that our car initially starts at 0 meters per second, reaches a maximum at about 5 seconds in, and then goes back down to 0 meters per second after 10 seconds. And what is our goal here? Our goal is to find the total distance that our car has traveled. And to do this, we need to take the integral of our function, or we need to find the area under the graph. But what does that mean? We're cutting our area into segments that are separated by a time interval. We can do it at 1 second time intervals, we can do it at half a second time intervals, or even a quarter second time intervals. But our goal is to eventually make our time interval so small that it approaches 0, so that all that empty space disappears and it basically looks like we've just shaded all the area under the graph. But what does this look like mathematically? Well, we can write that our area is equal to the integral, that squiggly line from our limits 0 to 10 of v multiplied by dt. It's very important that when evaluating an integral, you write this dt because this is like that plus c. If you forget this integral means nothing and you're going to lose marks, and your teacher may even give you 0 marks for the question if they're a bit mean. Now, what we're going to do is we want to find the function at which, when derived, gives us this t bracket 5 take a half a t, but that's a bit difficult to picture in your head, so let's make it a bit easier. We're going to expand these brackets. We're going to say 5t take a half t squared, and we're going to sub that into our integral expression. So our area is equal to the integral from 0 to 10 of 5t take a half t squared dt. Now this part is what matters most. We're going to evaluate our integrals, so we're going to write close brackets. So let's break it up into both of them. So we're going to start off with the 5t. What, when derived, gives us 5t? Well, I can see that it's 5t to the power of 1. So the expression prior to that was something t squared. Okay, so that means, and if we derive that, we're multiplying something by 2. So what multiplied by 2 gives us 5? Well, that's just 5 on 2. So writing that, we have 5 on 2t squared. And our next expression, minus a half t squared. That means that the expression prior was something t to the cubed. And deriving that, we multiply something by 3. So what multiplied by 3 gives us a half? Well, it's minus 1 on 6t cubed. And that's the process. This is how this works. and you just close the brackets and write your bounds. And now we are evaluating, as I showed at the start, how you do with a definite integral. We now evaluate our function at our upper bound, which means just sub 10 in for our t. So we write, okay, open bracket, 5 on 2, 10 squared, take 1 on 6, 10 cubed, close brackets. Subtract our lower bound. We write open bracket, 5 on 2, 0 squared, take 6, 0 cubed, close brackets. So our first expression is just going to evaluate to 250 on 8. And our second expression is just two numbers multiplied by 0 and then subtracting them from one another, which is just 0. So 250 on 8, take 0. Okay, so forgetting about the 0, we're just going to be left with the 250 on 8. So that means that our area is equal to 250 on 8, which is roughly 83.33. And in the context of our question, that means that our total distance is equal to 83.33 meters. Now, if you want to check this, I have videos on my channel showing you how to use your calculator, your graphics calculator, to solve definite integrals, and I'd recommend go giving that a check. I hope you enjoyed this video, and if you found it helpful, please let me know down below in the comments. And if you didn't find it helpful and you thought it was pretty shit, let me know down below in the comments. And just want to say thank you for 20 subscribers, really appreciate it. And if you could, please like and subscribe, because it just helps other people find these videos and it helps them learn along the way as well. All right, ciao.